Hey everyone, welcome to the fifth episode in our series of math team problems you should know how to do. Today we're going to be looking at a pretty in-depth introduction to the world of combinatorics. We've mentioned combinatorics before, but we're going to take a little bit of a deeper dive into them now. So what is combinatorics? The formal definition is the branch of mathematics dealing with the combinations of objects belonging to a finite set in accordance with certain constraints, such as those of graph theory. Yada yada yada. It just means counting stuff, but like with math. Um, it comes up a lot on math team contests in problems involving possibilities or probability. Like it comes up like a lot. So it's really important to have at least a basic understanding of kind of the general principles behind these kind of problems. So let's break it down. There are two major sections of combinatorics that I'm going to review. There are permutations and combinations, and then at the very end I'm going to do just a little bit about probability because combinatorics often will come up in conjunction with a probability problem. So without any further ado, here we go. Let's talk about arranging things. Here's the problem. How many different four-letter words, which just means arrangements, can be made from using the letters A, F, M, and R using each letter once? Well, we could try writing a list, which is possible, but super tedious, even with only four letters. If you had 5 or 6, quickly becomes extremely hard to do in any reasonable amount of time. So that's going to be a better way to do it. Remember those problems from elementary school, or if you're in elementary school, you've probably seen these, where it gives you like a menu at a restaurant and asks you how many meals of an appetizer, an entree, and a dessert are possible to like create with that menu. Well, we're going to address this a similar way. If we think of a four-letter word as 4 open boxes, then we know that we're going to have 4 letters that can go into the first one, so 4 options for the first one. Once we've chosen that first letter, it doesn't matter which one it is, there are only 3 remaining, so there's 3 options for the next, 2 options for the last, or 2 options for this next one, and 1 option for the last one. So if we multiply all these options together, we get the total number of words. It's the options for the first times the options for the second, so we end up multiplying to find all the possibilities. So there's actually an operation for this multiplying where it goes 4 times 3 times 2 times 1. We call it factorial. It's represented by an exclamation point right after the number. So 4 factorial equals 4 times 3 times 2 times 1, or 24. So there are 24 words possible for this problem. Awesome. Let's talk about some complications to this process. The first complication is that of repeated elements. If the set that we're organizing has multiple copies of the same element, that will change the result. For instance, if you swap 2 of the T's in the word frittata, the word doesn't change, so those don't count as separate arrangements. So we first get all the arrangements with 8 factorial, pretty easy. There are 8 letters, 8 factorial gives us the total arrangements of those letters. Now, here's the trickier part. There are 3 factorial arrangements of 3 letters. So there are 3 factorial arrangements of 3 T's in a row, but they're all indistinguishable from each other. So when they're distributed throughout a word, there are still 3 factorial arrangements of those T's. So if we divide the total word by 3 factorial, all of those different arrangements that have the T's just swapped around become one arrangement. So if we divide by the number of ways the T's can be shifted around, we can reduce all those identical words to just 1. There are also 2 A's, so we divide by 2 factorial to get rid of all the identical words that have the A's flipped. The general formula is total letters factorial divided by the factorial of each repeated element, those multiplied together in the denominator. Another complication can come in circles. So let's think about the question, in how many orders can 10 people sit around a circular table? We know that 10 people in a line have 10 factorial possible orders. But what we have to realize is that because the table is circular, any rotation of one order is really the same order. In the example I just showed, the table was rotated 1 space clockwise, which really ends up as the same order because everybody's sitting next to the same people. So if we divide our total 10 factorial orders by 10, we end up with 9 factorial as our total number of arrangements. There's one more complication I want to talk about. It's maybe the most important one, so we're going to go into the most detail. Let's say I have 19 books and I want to arrange 7 of them on a shelf. How many orders are possible? The important factor in this question is that the number of items being ordered, 7, does not equal the total number of items. which is 19. So let's start with our boxes strategy, making 7 boxes. You might be tempted to say 7 factorial and be done, but you'd be wrong, because there aren't actually 7 options for the first book. There are 19. And then there are 18 for the next, and so on. But then it ends with 13, and that's fine. 19 factorial is just 19 times 18 times 17 all the way down, right? If we don't like part of that line, aka the 12 times 11 times 10 times that part, we can divide it out. So what we end up with is 19 factorial divided by 12 factorial gives us 19 times 18 times 17, ending at 13. Let's try to generalize this. If we call the total number of items being ordered 7, which is 7, now we're going to call it R, and the total number of items n factorial over n minus r factorial should give us the total possible orders, which is pretty neat. That was a lot of math real quick. Take a minute, rewatch if you have to. I'm going to review some terminology and then we're going to move on. So what we've just been covering are called permutations. In counting permutations, the order of the element matters. For example, making a line of students. What we're about to talk about are combinations. In a combination, the order of the elements doesn't matter, like choosing a group of students from an entire class. A group of Sue, Bobby, and Fred is the same as a group of Bobby, Fred, and Sue. Order doesn't matter. In general, look for permutations in problems that are about arrangements or order, and combinations in problems about groupings or choices. Alright, let's move on. We're going to talk about combinations. Here we go. Count Ing of the nation of Combi must choose a delegation of 3 of his 10 advisors to represent him at the Grand Council. How many possible combinations of 3 advisors are possible? Let's start with our permutations idea and put down 10 factorial over 7 factorial. Because there are 10 options for the first advisor, 9 for the second, and 8 for the third, right? So we have that. We're not done yet, though. The thing to realize is that, again, order doesn't matter. So advisors A, B, and C are the same delegation as B, C, and A. We know that there are 3 factorial arrangements of any 3 advisors. So we divide by the number of arrangements of those advisors because any grouping of the same 3 counts as the same delegation. What we end up with is 10 factorial over 7 factorial times 3 factorial. So how do we generalize this? When we had 10 factorial over 7 factorial, we generalized it to n factorial over n minus r factorial. We can then generalize our new formula, 10 factorial over 7 factorial times 3 factorial, to n factorial over n minus r factorial times r factorial, because there are r factorial arrangements of those pieces being ordered. We've just derived 2 very important functions. They have names. The first one we found was called the permutation function, or n permute r. That's the n factorial over n minus r factorial function. The second one we found was the combination function, or n choose r. That was the n factorial over n minus r factorial times r factorial. But what if we're ordering the entire set? Here's what I'm getting at. These work in any situation. These functions will always work to give you permutations or combinations, respectively. But you might be looking at the permutation one and be saying, oh, what if I'm ordering the entire set? So if I have 19 books and I want to order 19 of them, then I have 0 factorial in the denominator. How does that work? 0 factorial actually comes out to 1. We'll prove that in a future video. But for now, these work in all scenarios, and you can use them in any scenario involving permutations or combinations. They're very useful. Let's do one more challenge problem before we go. This one might not seem related at first. I promise you it is. Uncle Aaron has $20 that he wants to distribute randomly among his 4 nephews and nieces. The kids don't all need to get the same amount, but each kid needs to get a natural number of dollars. How many ways can Uncle Aaron distribute his cash? In case you don't know, natural numbers are like the traditional counting numbers, 1, 2, 3, basically integers greater than or equal to 1. I'd encourage you to pause the video, try to work it out for yourself first. If that's not your style or if you're done, here's the answer. Let's imagine our $20 in a line. There are 19 spaces in between them. We're going to focus on those spaces. Any set can be divided into 4 parts by 3 vertical lines, right? So we just need some way to calculate the possible positions of those vertical lines. What if we chose 3 of the spaces in between the dollars to have those vertical lines. That would divide the space into 4 parts, right? It would eliminate duplicate divisions because the bars can be ordered anyway, but we're accounting for that with the dividing by 3 factorial. And it would make sure that everyone gets at least $1 because you couldn't put a bar on either on the far ends. So there we go. 19 choose 3, or 19 factorial over 16 factorial times 3 factorial is our answer. If you're wondering, that computes out to 969. I promised you I'd go over probability. This video is getting a bit long, so we're going to go really quick through this. Basically, all probability is just satisfying outcomes, which are those that meet the criteria, divided by the total possible outcomes. If a probability problem seems difficult with fraction multiplication, try breaking it apart to calculate each one separately. That's kind of my best advice for probability stuff, is if you can calculate satisfying and then calculate total, you can still get the probability. You don't have to do it all with fractions. You might have to do a permutation for one and a combination for the other, or something like that. Combination for one, permutation for the other, anything like that. That's all there is, really. No special trick. Just see how you can break the problem apart into problems that you know how to solve. Best advice I can give is practice, so that when you see a problem that is similar to one you've completed before, you can kind of not be trying it for the first time on a contest. Alright, that was a lot. Hope I was able to demystify some of the basics of counting and combinatorics. Check back later for more videos, and peace out, math people.